In this video, I'm going to walk through the Base64 assignment from beginning to end, looking at the skeleton code that was provided in the GitHub repository with the assignment. So before I get started, I want to highlight some key features of the skeleton code and explain what their purpose is. So on the first line here, we have a preprocessor defined for the POSIX source macro. It's being set to the value 2008-09L, which is referring to September 2008, when the particular version of POSIX that we are using was released. What this macro does, it's called a feature test macro. In all of these system header files for the C standard library, there are additional features on top of the C standard library that were added by POSIX. And in order to access those, you have to have the appropriate POSIX source feature test macro defined before including those files. So inside of each of those files, there's going to be a preprocessor condition based on this macro's value, and depending on whether it is set or not, or what value it has, will determine whether that particular function or object is exposed through that header file. So it's important to always put this at the top of our source code in this class, because we are using this particular standard of POSIX. Following that, we of course have all of these include directives for the system headers for various portions of the C standard library. So these expose all of the declarations for functions and objects that we want to use in our program. Following that, we have a separate block of include directives for local headers. So this is a multi-source project due to the gprintf, if you choose to use it in the assignment. And so we have the gprintf.c file, which implements the gprintf function, and then we have the gprintf.h file, which simply declares the interface for that function. So in order to use that function, you have to have a declaration of it before its use. And so by including this header file, we're also including that declaration into our source code so that we don't have to manually declare it. And the same is true for all of these header files. They are only providing declarations for things that are defined in other source files elsewhere. And we could actually replace all of these headers with our own manually written declarations of every function and object that we want to use from another source, but that would lead to maintenance issues and all kinds of other problems with having to manually track all of that. So that's why we use header files like this. So the header file defines the interface or describes the interface, and then we have source files that define the actual implementation. So next, after the includes, which should always go at the top of your program, by the way, before anything else, especially the standard library includes are required to go before everything else except for feature test macros like this. So just keep that in mind. And after the include statements or directives, we have a declaration and definition of this static character constant array called B64A, which is short for Base64 alphabet. So here at the top level, this static keyword signifies that the linkage of the Base64A identifier should be internal. So what that means is you can have either an identifier can either be internally linked, externally linked, or have no linkage at all. So an externally linked identifier is one that is visible in other contexts outside of this source file. So when you have a project that has multiple source files, each one is compiled independently, and then all of the externally linked identifiers in each source file are exposed. And when you go to link all of those compiled object files together into a single executable, all of the missing references in one file that reference an identifier that's provided by another file are resolved by the linker. And so it's only possible if the identifier in the other file is externally linked. Now, an internally linked identifier is one which is visible in the entirety of the source code file in which it's contained, but is not visible in other source code files when linked together. So generally we use internally linked identifiers for objects and functions that are part of an implementation detail, and externally linked identifiers are part of the actual interface of the program or the implementation that you're providing. And then lastly, we have identifiers with no linkage. So that's things like automatic variables. So like, for example, the arguments to the main function here do not have any linkage, and they can't have linkage. They always are only visible within the context of the main function. Same for this integer I in the for loop, has no linkage and never can. But here at the top level, anything declared at the outermost scope of a source file always has either internal or external linkage. External by default, so we use the static keyword to specify that it should be internal. And this is because we don't need to expose this to other source files, so we're going to be using it internally here in this single file. Okay, so that's why we have the static. Char is because this is a array of characters, and specifically ASCII characters, so printable text, which is why we use char. If you want to have an 8-bit arithmetic type, you don't use char, you use either unsigned or signed char. And char itself without an unsigned or signed specifier is actually a unique special type in C that is specifically for holding character codes of printable ASCII text like this. Next we have the constant qualifier, which applies to the char to its left. So we're basically saying that none of these characters can be modified, they're constant, and it would be a constraint violation to do so. Then we have the name of the identifier, and then we modify all of this by saying that we're creating an array. And so in C, when we're reading the type of a declaration, we always read, it's called the spiral rule. So you read to the right and then to the left. And so in this case, we would read this as Base64A is an array of constant characters with static storage duration and linkage, an internal linkage. And if there are parentheses around anything, you read to the right parentheses and then, or the right parenthesis, and then you read from the identifier to the left parenthesis, and then you go back to, you treat that entire parenthetical as a single atom, and then you read from the right side of it outward until the next parenthesis or the end of the declaration, and then you read to the left, and so on and so forth. So that's why it kind of follows a spiral, because you go out and then out again and out again until you finish reading the entire declaration. Now on the right side here we have a string literal, but this is actually a special case of a string literal. So only when declaring a character array, a string literal has a special meaning in that it is used to populate the contents of that character array. And it is the equivalent to enclosing this in curly braces and individually listing each and every single one of these characters as a character constant separated by commas. So it is only provided as a shorthand for that, and it is different than anywhere else you would see a string literal. So for example, here, this string literal actually represents an object, an anonymous object, an unnamed object, which is created by the compiler and then referenced with a pointer here. So this will be replaced with a pointer to an object that contains this data. In this case, that's not what happens. Instead, we're just directly initializing this array with this value. And so there is no anonymous object, and this is not pointing to it. So it's a little bit different, and it's only the case with a character array that this occurs. Now with a character array being initialized with a string literal like this, you can either specify that the array has an unspecified size. So here we don't provide a size for the array. The compiler will automatically determine the size as being large enough to fit all of the characters in this string plus a terminating null byte. So in this case, it should be 65 characters. As an option, you can manually specify the size of the array to be one less than that, in which case the terminating null byte will not be included in the array. Or you can make it larger. You can make it as large as you want, it doesn't matter, because any extra space at the end of the array would be initialized to a 0, a null byte, because of the rules of array initialization. Since you've already provided at least one member of the array, or one element of the array, all remaining elements will be set to 0, if not explicitly defined. And then here we also see a nice feature of the preprocessor, which is that adjacent string literals that are separated only by white space are actually concatenated. So this is actually one long string split into 4 lines for readability purposes. In general, though, this is something that you want to be careful about. So usually we have kind of a line length limit when we're writing in C, but that limit usually doesn't apply to strings like this, because if an error were to occur and this message were printed, somebody might want to look in the source code, search the source code for that particular error message, and if you break it up onto multiple string literals, it can be very hard to find. So generally with error messages, they're always left as one contiguous string, even if it would span many more columns than the typical column limit. But for things like this, it's much more common to split it up like this. Okay, so that's our alphabet. And then we have the main function. So the main function is required, there is required to be an externally linked main function in any executable C program. And it has to be a function which returns an integer, and it either takes no arguments or it takes 2 arguments, an integer and an array of character pointers, or pointers to characters. And typically these are called argc for argcount and argv for argument vector. Additionally, there are implementation defined extensions on this. So for example, in POSIX, you can actually have a third argument for the environment pointers. So this would be pointers to all of the environment variables that are inherited from the parent process, but we don't need to worry about those right now. So this is sort of the standard declaration for the main function. And again, the reason we don't have static here is because the main function is required to be externally linked, not internally linked, so that it can actually be executed in the first place. If it was internally linked to this source file, then the C runtime would not be able to execute your main function because it wouldn't know where to find it. So it's externally linked. And then here we just have a couple of example usages of some basic functionality. So here we have printf being used to format this format string here and replace this with the alphabet defined up here so we can see what that is. One very important thing that I want to point out is that you would never want to do something like this. If you wanted to just use printf to print a variable that contains a string, you should always use the format specifier like this, because your string itself could contain a escape character recognized by printf. So for example, if the Base64 alphabet had a % in it, it could cause problems if you just used it as the first argument to printf. So that's a common mistake that beginners make, especially when this is like user input data of any kind. You can run into some serious problems there. So we have this example there of a printf statement, so I'll get rid of that. And then we also have this gprintf function, which was provided for you by the gprintf header and gprintf implementation local to this project. And basically all this is it's basically printf, but it gets turned off in the release build. So one thing that I see a lot of students do in the beginning is they'll pepper their code with printf statements to debug it, to see what the values of variables are and things. And then when they go to submit their assignment, they just comment all of those out. And that's a very messy way to go about debugging your code, and it requires a lot of manual intervention to comment and uncomment things. So it's much better to have a specialized function like this that gets turned on or off depending on the value of a preprocessor macro. And then when you actually compile a program, you can pass macro values in on the command line, so you can compile different versions of your program based on different macro values. And that's actually one of the main purposes of macros in general, is to turn on or off certain features at compile time. So large pieces of software will often have features like this. For example, Vim has many of these features that can be turned on or off via preprocessor macros at compile time, such as clipboard support, graphics support, things like that. So gprintf will show up only in the debug build, but it will not show up in the release build, which is what is tested on Gradescope as well. Next we have an assert. So assert is another debug-only macro. So it's provided as part of the C standard library, and assert.h is where it's defined. And essentially, an assert, it's a function-like macro, and in your debug build, if this expression evaluates to 0 or a false value, then the program will abort and print the cause of the termination, essentially. In the release build, assert statements compile to a non-operation. So they're only there for debugging purposes in a debug build for the programmer's benefit. And assert statements are used to verify constraints. So for example, your function, you might write a function that's used internally, and it requires the caller to ensure that it never receives a null pointer. So you can add an assert statement at the beginning of that function to check that that pointer is not null. And this avoids having to have an if pointer equals null check in your production release code instead. So we have that feature that's very useful, and then we have another put s, which is another way to print a string, and conveniently adds a new line to the end in this function. So that can also be sometimes more useful than printf. I think students tend to think of printf kind of like a hammer and everything's a nail. So this is another option if you just have a simple string to print. And then we have a return statement for main. and we're returning the value exit success. So exit success, by the way, is equivalent. It's basic. It's 0. And there's also exit failure, I could spell, which is 1. And technically, according to the C standard, these could be different, but in pretty much every implementation that exists, 0 is a successful exit. It turns out that if you leave a return statement off of the end of main, it will automatically return 0 as well. And so it's basically the same as a successful exit. And this indicates to the caller of the program itself, it's returned as the status of the process after it executes, and it basically indicates whether an error occurred, and maybe potentially specifies what kind of error, although it's also very typical to only return a value of 1 in the event of an error. And whoever ran the program has to look at an error message to see what went wrong. It's pretty rare for a program to use different values, different status values to indicate different types of errors. So that's the basic skeleton code, and let's go ahead and get started. So the way I would recommend going about writing this program is to first focus on reading from standard in, and then add the functionality for reading from a file later. And we can do that using reopen to reopen standard in, but point it at a different file. So we can write all of our code kind of agnostic to that. So let's go ahead and get started. So the basic structural layout of our program is going to be an infinite loop with some kind of an exit condition. The exit condition is going to be we ran out of data on the input side. And just to note, you can't do this. This is always wrong, and the reason is because this end of file flag is not set when the program is invoked. So it's not necessarily, it's neither set nor unset. It's an indeterminate state. So you can't really check it until you've actually attempted to perform a read operation on the stream in question. So this is pretty much always wrong unless you did read something up above the for loop, but we're not going to do that. So instead, you have to have some kind of a break statement inside of your loop to exit. And this is very common in C. I know in other languages it might be frowned upon to have control to exit a loop in the middle and things like that, but this is how it's done in C, so you just have to get used to it. So what we're going to be doing to implement the Base64 algorithm, if you look at the Base 8 code, it's pretty similar. We need to operate on chunks of 3 bytes at a time in order to get 24 bits, because the Base64 alphabet encodes 6 bits at a time. And so the least common multiple of 8 and 6 is 24. 24 bits, that's 3 bytes. So that's how many we need in order to get 4 Base64 digits of output at a time. If we were to read less than that, we would have to kind of keep track of the extra bits left over from the previous read operation. So it would be a little bit messy. So we'll go ahead and, oh my gosh, can't type today. We will declare our character buffer, and it is an unsigned character buffer because we're reading in raw bytes, not ASCII characters. Okay, this is very important. We're reading in numerical values in the range 0 to 255 inclusive, which represent arbitrary data bytes from standard in. And then fread returns a size t. I always forget that one. And fread takes two arguments here in the middle. So the first one is the size of an element, and the second is the number of elements. And this is kind of a historical throwback. So if you have like an array of structs or something, it might make sense to put the size of each element as the size of a struct, and then the number of elements here as the number of elements in the array. But there's not really an advantage to doing this. On the back end, fread actually just multiplies those two values together no matter what. The downside to having this not be 1 is that the return value of fread is the number of elements read successfully. So if there's an error here, if something goes wrong and the element size is greater than 1, then we don't know if that last element was partially read or what, because it could have been some number of bytes, but not the full number of bytes required for that size. So for that reason, it's pretty much universal that the second argument here to fread is always 1, and then this is just the size of the buffer that's being written into, or however many bytes you want, as the third argument here. And just another note, size of is an operator. It's a unary operator. It is not a function, so I'd never want to see this. Okay? It's the equivalent of writing something like that. You don't need parentheses around your operator operands. Now, the only exception to this is that when you are explicitly giving the type of something, you have to surround the type in parentheses. But there should still be a space here, stylistically, because this is an operator that typically has a space after it. So it would be kind of strange. It's kind of the equivalent. It's kind of similar to writing x plus y everywhere, but then writing x plus y and removing the space when there's parentheses involved. So stylistically, it should always have a space there. And also, just as a note, you pretty much should never have, you should almost never use the size of operator to get the size of a type. You're almost always using it on an object itself, in this case buff. And the reason for that is because if the type of buff was ever changed, like if I changed this to an unsigned integer or something, then this would automatically update itself here. But if I said something like this, I don't even know, something along those lines, size of char times 3, or something like that, then it wouldn't accommodate changes in the actual type of the thing that we're referring to, and therefore you could have bugs introduced as a result. So size of, always use it with an actual object if you can, and avoid using it on a explicitly listed type. Okay. So now we have presumably read in some number of bytes into buff. And according to fread man page, if the number read is fewer than the number that was requested, it indicates two things. Either there was an error or we reached the end of the file. So the first thing we can check for is an error. So we can print some informative message about the failure that occurred. And this error function here will automatically print out a nicely formatted error message for us. The first argument is the exit value. So in this case, we want to exit 1 or exit failure. And then this is the message, which is formatted as a printf style string, so you can add additional strings to it like that. Now, typically, when I print out errors about file I/O, I don't print out the name of the function like that. I actually print out the file name, and in this case, I'll go ahead and declare this file name variable up here for later when we change it so standard in can point anywhere, and then I will print out the name of that file. Okay, so, and conventionally a dash is used to represent standard input. Sometimes programs will put it in parentheses, you know, like parentheses standard in. There's different ways to write that, but a dash is pretty universally understood as well. Then the other scenario is if we've reached end of file. So if the number of red was less than the size of buff, there was an error we want to exit. That's the appropriate thing to do in that case. But if we reach the end of file, there's two possibilities. One is we didn't read anything at all, so NR is 0, in which case we do want to exit. Or we read something, but it wasn't 3 bytes, in which case we still need to process those remaining bytes and then exit. So we're basically going to have two locations where we could exit from this loop, one directly after the fread in the event that nothing was read, and one at the end of the loop in the event that something but not a full 3 bytes was read. So in this case, we can simply check if NR is equal to 0, we can break. And we can assume here that if NR is equal to 0, that the standard in flag is set in this case. And the reason for that is because if NR is equal to 0, we would have gone through here and checked F error. And so at this point, if NR is 0, F error can't be set. Therefore, end of file must be set, because those two conditions are one or the other must have occurred to get a short read. So we don't really have to check it. And we can also kind of combine these two separate if statements into one, like this, just to clean things up a little bit. So now we have our two conditions. So if we read less than expected and there was an error, we're going to exit. If we read exactly 0 bytes, we'll break and we'll exit normally. And then here we'll go ahead and start processing our data. And there are a few different ways that this can be accomplished. We could do this in multiple stages. We could first convert each character. We could extract 6 bits at a time and convert that to an index, and then save that in an array, and then convert each index into a character in the Base64 alphabet, and save that to an array, and then print that out. And we can also use a nice little trick that I've demonstrated in the Base8 code to first combine all of our input bytes into a single into a single integer, and then we can easily use the same process over and over to extract 6 bits at a time, which is a little bit easier conceptually compared to trying to take the upper 6 bits of the first character and then the lower 2 bits of the first character and the upper 4 bits of the second, and so on and so forth. So there are a couple different ways to do it, and they all have different trade-offs in terms of complexity. But let's go ahead and do the example from base 8. So it turns out that we have 24 bits here, and a long unsigned int can hold, I believe it's 32 is the minimum size of it. It's usually 64 bits, but the standards require it to be at least 32. And so it can hold all 24 bits, which is really convenient because it makes it a lot easier to work on this data if it's all contained within one contiguous sequence of bits in one piece of data. So we'll go ahead and do it that way, and essentially each byte that we've read in, we'll push that into this integer here. So we'll add the first byte, buff0, and then we'll shift it 8 bits. Here I'm going to use the char bit macro, which is defined in limits. And technically in the C standard, this can be anything. It has to be at least 8, but the C standard actually allows for systems where it's 16 or 32 or even some odd number like 24. But POSIX requires it to be 8. So since we're writing a POSIX program, we can kind of just gloss over that fact. You can also, if you want to be really careful, you can add a check here at the beginning with the preprocessor, like this. It will never, on any modern system, this will never occur. It's very, very rare to find a system where char bit is not 8. But it's nice to use the macro when you can instead of hard coding a value of 8 here. Okay. And then so we basically just repeat this operation for each. Oh my gosh, I'm having trouble today. So essentially what we're doing is we're putting the byte value of each byte in the buffer into bits, into the lower 8 bits of bits, and then we're shifting everything over to the left that much, and then we're putting in the next one. Just like this. Okay, so we'll end up with all of our bits loaded in. So if this was sort of like, if buff0, we represented this as, if we enumerate all our bits with the alphabet, we'll have A, B, C, D, E, F, G, H, right? 8 bits. And then what we'll end up with is some number of zeros, and then A, B, C, D, E, F, G, H, like that. And then here, we'll shift it all to the left, so we'll have zeros, some number of zeros, and then 1, 2, 3, 4, 5, 6, 7, 8 zeros. And then this will I, J, K, L, M, N, O, P. Like that, so it'll replace those zeros, and then this one will shift it again, so we'll end up with some zeros, and then A, B, C, D, E, F, G, H, I, J, K, L, P, 1, 2, 3, 4, 5, 6, 7, 8. Okay, just like this, and then finally we'll end up with, I think you can see where this is going. Oh, that's buff 1 here. Q, R, S, T, U, V, W, X. And that's A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S. Just like that. Okay. So that's what we'll be left with. We'll have some leading zeros, probably 8. So if this is 32 bits total, we'll say that's 8. Okay. Just like that. Now we can go ahead and extract 6 bits at a time from this. And each of those 6 bits will represent the index in our Base64 alphabet. So we can have a Base64 index array. We'll have 4 integer values representing the index into this alphabet. So each of these will be 6 bits. So we could use like unsigned char if we want, because that's a 8-bit data type which can hold all 6 bits of the index. So maybe I'll use that instead of an int. It doesn't really matter because all of our integral data types that we have the ability to hold this 6-bit index value. Signed char does, unsigned char, integer, and everything else can all hold it. So it doesn't actually matter very much what data type we use here, because we're just storing an integer value based on the 6 lower bits that we're extracting. Okay, and then we actually have to put these 6 bits in the first element of this array, and then the next 6 bits in the second, and so on and so forth. So this is actually going to be the last 6 bits of our output. So we want to maintain that order. And so probably the easiest way to do this is actually to work backwards, just like this. And we're going to yeah, it doesn't really matter. Okay. So basically what we do is we mask off all but the lower 6 bits of this bits integer here. So we're going to AND it with the value 3f, which is 6 ones. And then that's going to essentially zero out all of these bits up here and leave us with just these 6. Okay, so that'll be the first one. And then we take bits and we shift it to the right 6, and then we do the next one. And I think hopefully it's obvious that this would be really nice to do with a loop, but I'm just writing it out like this to really demonstrate the math that we're doing so that everybody understands it pretty well. Okay, and then for the last one, we don't need to mask it because it's already, all of these zeros have been shifted in, and so we basically just have a 0, 0, 0, 0, 0, all the way up, A, B, C, D, E, F, so we don't need to mask the last one. Okay, and so those are all of our indices, and then finally we'll have a character array. I'll call this Base64 output. That was Base64 indices, by the way. I like my abbreviations. And so in this case, we do need to use the char data type because that's for holding ASCII text specifically. And here we're just going to do, it's very simple. We'll look up in the alphabet based on that index. Just like this. Oh, it doesn't like that. Okay, and so that will set each of those, and then we simply just fwrite to standard out, just like that. So that's the basic skeleton of our Base64 encoding. Now we do have a couple of other things that we need to account for. One is if we read less than we were expecting, then we need to deal with padding. And the padding bits, first of all, we go through the normal process of encoding as if the missing bytes were 0. So the first thing that we need to do is we need to ensure that those are 0 for our encoding to work properly. So I'm going to initialize this array up at the top to all 0s. So I'm initializing the first element, and then all of the other ones are automatically initialized to 0. So that's why you see this notation a lot in C. So that's going to zero it out and ensure that all of this math works properly. And then the last thing that we have to do is then replace either the last or the 2 final characters of output with an equal sign, depending on the number of characters that were read. And so if nr is less than 3, then the number of padding characters is at least 1, so we can go ahead and unconditionally set this to an equal sign. And then if it's less than 2, so it's 0 or 1, Base64 output 2 is going to be an equal sign. Okay. So this handles all of the possible cases here. Just keep in mind that we would never reach this point if nr was 0, because we would have broken up here. So we've kind of handled that case. And then here we're handling the case where it's 1, also the case where it's 1, and then we're handling the case where it's 2. And then if it's 3, then we don't need to worry about padding at all. So we've got all of those cases covered. And we've got our output just like we want. Now, the last thing that we have to deal with is our wrapping. So, well, I guess we also have the file, but let's deal with the wrapping first. So we're supposed to wrap at every 76th character. So after 76 characters of output, we want to output a new line character. And one problem is that we need to do this potentially after the for loop exits. So the reason for that is because we could break here after having output part of a line, but not an entire line. And so then after the for loop, we might want to print out another new line. So one solution is, before breaking, we could add some extra code to check to see if we have to print out a new line. We'll also have to do that down here as well. So before I forget, I'm going to add a break here. So again, remember we have 2 break locations. We have one here if there was no input because we reached end of file. And then here we have the second case of there was some input, but not a full 3. So we guaranteed that we've reached the end of file. So we could have a redundant check here. Standard in. We could put a redundant check for end of file on standard in if we wanted, but we are guaranteed by the description of fread, if nr is less than 3, either an error or end of file occurred. And since we've checked for an error, we know that any of the other instances indicate end of file, so we don't have to check them. You can also have both. You could have end of file and an error technically, but we'll handle the error and not worry about the end of file. So we have two break locations. When we're dealing with wrapping, we could handle that last new line at both locations, which is a little bit messy, or we could handle it after breaking, which is generally preferred because you don't want to repeat yourself. That's a rule in programming, right? Don't repeat yourself dry. And so in order to accomplish that, we'll have to have a variable to track the number of characters in the current line that exists outside the scope of the for loop. So I'll go ahead and declare that up here. And of course, it's initialized to 0. And then down here, after our fwrite, we will increment it by 4. Or we can do the size of if we want. It would be fine, by the way, to replace this with 4 if you wanted. It's a little different when you're dealing with, in this case, the Base64 algorithm specifically. We're specifically treating each individual element of this array as a separate variable almost. So if you want to hard code it as 4 or 3 up here, that's fine, because it's like sort of part of the specification itself that number is what it should be. But either way, so what we're doing, and then we'll check if it's greater than or equal to 76, right? Why not check greater as well as equal? It doesn't cost us anything and helps avoid any weird bugs. We could add an assert here, for example, to make sure that it equals 76. That's nice. Let's do that. And then what we want to do is we set line char back to 0, and then we put a new line. Done. Very, very straightforward, right? One thing that I see sometimes is like this, and you always want to avoid that. Don't use modular arithmetic if you don't have to. One, it's very expensive. This is a division operation, which is the most expensive operation that you can really do on a processor regarding integers. And then on top of that, another big mistake I see with modular arithmetic a lot is that students will forget to set the counter variable back to 0. And that's a problem because eventually your counter can actually reach its maximum value and overflow, and that's undefined behavior. So just check against the maximum value and be done with it. Don't worry about being fancy. And then here outside of the for loop, we have to basically check this condition, but in the reverse. So let's say we printed out part of the last line, and of course we haven't yet printed out a new line. So the way we would check that, if line char is not 0, we'll put a new line character on standard out, right? So if it's 0, it means we've printed exactly 0 or more complete lines, and if it's non-zero, it means we've got one line that we're still working on. So that handles that case for us, and now the last thing we have to do is handle the arguments of the program itself. So if we go ahead and check our arguments, so the first one we can check is if argc is greater than 2, well, that's an error. And I like to just set it to enval and then use the error function, and this is invalid value. So it's basically the error code for an invalid argument. So by setting it before calling error, it sets the message that will be printed with the error message, which is kind of nice. Yeah, so that works fine. You can also do like a usage message. This is also, you can use the error X to not print out an additional error string and just print out your message and exit. And you could print something like this. And then, let's see. So that's the error case, and then here's the case where we have an argument. Remember, argc is the total number of arguments, where the first argument, argv0, is actually the name of the program itself. So in this case, we have a program that takes in one argument. So when argc is 2, we have one argument to our program, and it's stored in argv1. Okay, so fn is now argv1 instead of a dash, and then we're going to go ahead and try to open. We can say result. Try to open it for reading on standard in with freopen. So then we check to see if result is null, and if so, we'll print out an error about our file, just like that. We'll just print out the name of the file and the error. Otherwise, standard in has been reopened and we're good to go. And here we've referred to it by the file name and not standard in hard-coded, so it should be good. And then, so one thing is, some of you might wonder, why don't I check the return value of fwrite or putchar? And the reason for that is because in general, you don't really need to check if output was successful. It's sort of, it sort of depends on the type of program you're writing. In this case, we don't need to check. It's sort of on the caller of the program to ensure that the destination of the output will work properly. Also, because we're redirecting standard in here to this other file with freopen, we're sort of, the C runtime is responsible for handling the standard streams. So we're not really required to deal with it ourselves. The C runtime will handle it. Now, if we were opening a file, what we might want to do is at the end, close it. And one thing I'm actually going to do is I'm going to add a flush here for standard out to make sure that the output's actually being written. So if we were opening a separate file and it wasn't being, and we weren't just reopening standard in and pointing it somewhere else, then when we close it at the end of the file, at the end of our source code, then we would kind of want to check to see if an error occurred, maybe. But one of the problems is that when an error occurs with file closing, or at the time that a file is closed, or even during a write operation, you can't necessarily fix that error. So it's sort of like an error that you would just catch and exit, but it doesn't really affect the program much if you keep trying to write to a messed up output stream. So it's kind of up to the programmer what they want to do. Sometimes adding a extra error check like that would slow the program down. And especially for something like this where you're trying to, convert data into a different format, you usually want to be as quick as possible. So coding for that common case of standard out working properly is generally preferred. Now, if you were writing something like a database program where you have like transactions, then you would actually want to check, right? Did an error occur on write? Did an error occur when we closed the file, etc.? And if so, you might want to like roll back to previous version or something, or undo whatever operation you just attempted to do so that you don't corrupt your database. So it kind of depends. But in general, we don't have to check output errors as often or as carefully as we check our input errors for issues. Right? You can see if there was an input error and you ignored it, you would have garbage data in buffer or all zeros or something, and then all kinds of weird stuff might happen. So that one you definitely need to check. But this one is kind of on the caller. All right, so let's go ahead and see if I did everything correctly here. And what is it? Build. Looks right to me. All right. That'll do it.